Hello everyone, my name is Chun-Wei. This is the part 4 video of the 6th quadcopter simulation and control project. So today I'm going to show you a small change of the path mode simulation model. Okay, so you can see here I upload all the new information on my website. And here you can see that what I'm going to demo today is a faster path. Okay, faster path. Okay. And I also do some change about the sampling rate, the time sampling rate. Okay. And this one, drone control path v2.zip, is the latest version, and which is going to the topic of this video today. Okay. So let's get straight into it. So here, the A, here I use sine 1t, cosine 1t, and sine 2t, so that the drone will move faster. Small correction here, do not change the TSS here, because later we are going to use the same TSS when we are going to generate the XYZ CMD. So instead of changing this, I recommend directly change this equation if you want. Okay. So I already run the script. So here are the A path metrics. Another new things I add into this demo is I want to show the stability of this drone. So after 35 seconds, I set the drone to always hover at 2 to 3 position to show you that the stability of this drone, how stable it is. Okay, so you can double click this to load it, and then you run the script to generate the exact XYZ CMD. And afterward is the same step. So go into the drone direct simulation and press 1. And here I'm going to show you the result of the animation. Here, okay, here you can see that it moves much faster because I specify a faster speed when we design the path. Okay. And I really want to show you the hovering process after 35 seconds. Okay. So as you can see, after 35 seconds, it will hover at 2 to 3 position. Another small changes I use in this version is that I set a pose signal to the yaw. I use this to demonstrate the control of yaw angle. Okay. The other big changes I use is in the controller. Okay. So I changed some of the structure of the controller. Okay. Previously, when we have the reference file, I use a single PD controller to transform the phi error into the torque. However, I found that there are some oscillation for this kind of control. Instead, I try to directly input the phi rates, okay, and use two P controller for this structure. And it's similar to this. It's really similar to this one. Okay. So here, if you open the torque scope, okay, if you run it, you can see that now it has a more practical control output signal. If you compare this one to the previous version, there are really a big difference. Okay. So that is why I changed the controller structure from a single PD controller to directly input the Euler rates. Also from the X controller, I changed the structure, and you can tell. So you can see it is a more practical and less oscillating output control signal. And the same for the yaw controller here. Okay. The last thing of the controller, the change of the controller, is that I set the sensor rate, also the reference rate, and the controller rate to 0.01 sampling time. Okay. So if you really want to check out the sampling time, you can go to here, debug, information, and colors. Okay, so here, the red line is 0.01 sampling rate, and the black is the continuous. So overall, the reference and the sensor and the controller will be set to 0.01 sampling rate. And for the 6-stop dynamics, it will be calculated in the continuous time domain. Okay. So the reason I add these changes, so for example, the sampling time rate and the change of the controller structure, is that I want to have a more realistic of thrust torque output. Okay, so I don't want too much oscillation like as for the previous model. And if we have this more realistic model, more practical controller signal output, then later we are able to compare this to the DNN neural network. What is DNN neural network? DNN neural network is the deep neural network controller. Because deep neural network controller has a sampling rate of 0.01 second, which I set. So I want to make sure that for all the controllers, if we want to compare them, we need to have the same sampling rate and the same oscillation changes, I think. So that is why I want to make these changes. Okay. Last thing, okay. Some of you are asking me, so what are the theory behind this project? What materials did I use to build this project? Okay, so if you go to the home page, here, actually, I really encourage you to read or to check out these two pages. First is a 3-dot quadcopter, and the second one is a star tracker. These are the two projects I practiced before doing the 6-dot. Okay, first 3-dot. Okay, so 3-dot quadcopter simulation control. This is how I practice how to control the translation of a 2D drone. And the equations of dynamics is really simple. It's just a 2D dynamics, and you can download it without any password. Okay, so here I practice how to control translation motion, and I practice how to generate signal, a CMD signal. Okay, and later I did the star tracker control and simulation. Okay, so these projects it's about the Euler angle, the Euler transformation from body frame to inertial frame, and how to control the attitude of a star tracker, which is a star spacecraft. Okay, and here are some demo, okay, of how to control the altitude. And over here, I provide some like basic theory of Euler transformation. So for example, we have the first inertial frame, and how can we transform to the vehicle 1 frame? By rotating, and the vehicle 2 frame, again, pitch rotates, and to the body frame to the from the roll rotate. And there are some concepts about gimbal lock, And also here are some example about how to transform to the inertia frame. These here are the reference I use when I build this project. They are really useful. Here are some basic altitude control demo. If you want, you can look at this. So the green is the target. The green altitude is the target altitude. And what I want to do is just to control the red to move to the green, axis. Okay. And here are some gimbal lock demonstration. Okay. You can see if the red is going to follow to the green, there might be some problems later. It's about gimbal lock. It's the limitation of using Euler transform. Okay, you can check it out. And here are some okay, here you can see as usual the green is the target altitude, and the red is trying to track the altitude. And this one is the linear solver, and here is another nonlinear solver. Okay, so you can see that this one can successfully track the green altitude. Okay, the linear solver and the nonlinear solver. So basically, I practice altitude control, Euler transform, and Euler angles in this project. And thanks for watching. And in next video, I'm going to talk about the wind disturbance. Thank you.